What if everything we know about the universe is just a tiny fragment of something far grander? Picture this: the night sky, endless and mysterious, dotted with galaxies that stretch beyond comprehension. Now, imagine those galaxies aren't just drifting in isolation, but might have once collided with another universe entirely. It sounds like science fiction, but what if it's real? The idea that our cosmos could have smashed into another, a multiverse collision, is one of the most mind-bending possibilities in modern physics. Think about it: the universe we call home, with all its stars, planets, and life, might have once tangled with another reality, leaving traces we're only now beginning to uncover. The concept of parallel universes isn't just wild speculation. For decades, scientists have wrestled with theories suggesting that our universe isn't alone, that beyond the edges of what we can see, other realms might exist, each with their own laws, their own histories, even their own versions of us. And if those universes are out there, what's stopping them from bumping into ours? The very fabric of space-time could bear scars from ancient collisions, subtle clues hidden in the cosmic microwave background, or the strange behavior of distant galaxies. These aren't just abstract ideas, they're puzzles that could redefine our understanding of reality itself. So, how would we even know if such a collision happened? What would it look like? Could it happen again? Buckle up, because we're about to dive into one of the most thrilling frontiers of science, where the boundaries between worlds blur and the universe we thought we knew becomes something far stranger. From cutting-edge simulations to mind-blowing mathematical models, researchers are piecing together evidence that might just rewrite the story of everything. This isn't just a tale of distant galaxies, it's a story about us, about how we fit into a cosmos that might be infinitely more vast and interconnected than we ever imagined. Stick around, because what comes next could change the way you see existence forever. To understand how our universe could collide with another, we first need to grasp the mind-bending foundation of multiverse theory itself. Imagine space not as a single, solitary expanse, but as one page in an infinite cosmic book. Each page its own universe, with its own rules, its own history, and maybe even its own version of you. This isn't just fantasy, it's a serious scientific frontier born from the quirks of quantum mechanics and the mind-stretching possibilities of string theory. Take quantum mechanics for starters. At the tiniest scales, particles behave in ways that defy common sense, existing in multiple states at once until observed, as if reality itself branches with every decision. Some physicists argue this isn't just a quirk but evidence of parallel realities splitting off endlessly, each one a new thread in the fabric of the multiverse. Then there's string theory, which suggests the universe isn't made of point-like particles but vibrating strings, and those strings could resonate across higher dimensions we can't perceive. In those hidden dimensions, entire universes might float like bubbles in a cosmic foam, occasionally brushing against one another. That's where the bubble universe hypothesis comes in. Picture the Big Bang not as a one-time event but as one of countless eruptions in an eternal cosmic landscape, each bubble inflating into its own universe with its own physics. Some might have stronger gravity, others no light at all, and a few, like ours, might be just right for life. Now, if these bubbles drift close enough, their edges could touch, creating shockwaves that ripple through space-time. Think of it like soap bubbles merging in a sink, gentle at first, but with enough force they might distort or even burst. A collision between universes could leave behind cosmic fingerprints, strange patterns in the microwave background radiation, unexplained voids in galaxy clusters, or even regions where the laws of physics seem to glitch. These aren't just abstract ideas, scientists are actively hunting for them, scanning the skies for anomalies that might rewrite our place in the multiverse. So when we talk about universes colliding, we're not just spinning sci-fi tales. We're peering into the deepest questions of existence, armed with math telescopes and quantum clues. And if the evidence stacks up, we might soon prove that our universe is just one voice in a grand cosmic chorus, forever echoing against the walls of reality itself. But how do you spot a cosmic crash that might have happened billions of years ago? The answer lies in the oldest light in the universe, the cosmic microwave background, or CMB. This faint glow, left over from the Big Bang, blankets the entire sky like a fossilized snapshot of the universe's infancy. And just as cracks in ancient pottery reveal its history, subtle irregularities in the CMB might hold clues to a violent encounter with another universe. Take the infamous cold spot, for instance, a mysterious region of space where temperatures dip unexpectedly, as if someone pressed a cosmic ice pack against the fabric of reality. At first glance, it might seem like random noise in the data, but some scientists think otherwise. Could this chilling anomaly be a bruise from a long-ago collision? Imagine two universes brushing past each other, their gravitational forces warping space-time like a trampoline dented by a falling weight. The energy drain from such an event could leave behind a cold patch, a ghostly imprint lingering in the CMB. Of course, not everyone's convinced. Skeptics argue the cold spot could just be a statistical fluke or the shadow of a vast cosmic void. But here's where it gets fascinating. Researchers have run simulations showing that a multiverse collision would produce patterns eerily similar to what we're seeing. It's like comparing a crime scene to a suspect's alibi. The CMB's irregularities fit the theoretical fingerprints of a universe-on-universe smash-up. And the cold spot isn't the only clue. The CMB's large-scale asymmetry, a lopsided distribution of hot and cold regions, hints that something fundamental might be off about our cosmic neighborhood. Some theories suggest this imbalance could be the gravitational echo of another universe tugging at ours in the distant past. Picture drifting continents on Earth, their collisions leave mountain ranges behind. Could the CMB's oddities be the cosmological equivalent, wrinkles in space-time from a fender bender with a parallel reality? The hunt for answers is driving some of the most ambitious experiments in astrophysics. Telescopes like the Planck satellite have mapped the CMB with unprecedented precision, while next-generation observatories aim to zoom in even further, searching for telltale swirls or distortions that conventional physics can't explain. Every anomaly, every outlier in the data is a potential breadcrumb leading us closer to the unthinkable, proof that our universe isn't just one story, but a single paragraph in an epic far grander than we've dared to dream. So the next time you gaze at the night sky, remember, it might not just be stars you're seeing. Hidden in that ancient light could be the scars of a cataclysm that reshaped existence itself, a whisper from beyond the edge of everything we know. And if we're right, the universe just got a whole lot stranger and a whole lot more interesting. That chilling patch of space known as the cold spot isn't just a cosmic oddity, it's a detective story written in the language of thermodynamics. Spanning nearly 200 million light-years across, this vast region in the constellation Eridanus registers significantly colder than its surroundings, as if the universe left its refrigerator door ajar. At first glance, it could be dismissed as cosmic static, a random fluctuation in the afterglow of the Big Bang. But when astronomers crunched the numbers, they found the odds of such an extreme anomaly occurring by chance alone were less than 2%. That's like rolling dice 100 times and never landing on 6 possible but eyebrow-raising. So what could explain this frosty enigma? One camp argues it's simply a colossal void, a sparse region of space where fewer galaxies and less matter create a natural temperature dip. Think of it as a cosmic desert where the lack of stars and gas allows energy to stretch thinner, cooling the space around it. Yet even this explanation has holes. Voids this large are rare, and the cold spot's temperature variations are more extreme than typical models predict. It's like finding a polar ice cap in the middle of a savanna. Something doesn't add up. Then there's the more electrifying possibility. The cold spot could be a scar from a multiverse collision. Picture two soap bubbles, our universe and another, grazing each other in the primordial chaos of creation. The gravitational tug of war between them might have siphoned energy away from our side of the boundary, leaving behind a cold, stretched region of space-time. Simulations show such an impact would create precisely the kind of temperature dip and concentric ripples we're observing. It's as if the universe bears a fingerprint and the ridges match the grip of another reality. But here's where the mystery deepens. If the cold spot is evidence of a collision, why don't we see more of them? Shouldn't the cosmos be littered with similar bruises? Some theorists suggest we might be looking at a unique vantage point, a single titanic clash frozen in time, like finding one bullet hole in a vast battlefield. Others propose that additional anomalies do exist, hidden in the noise of the cosmic microwave background, waiting for sharper telescopes to reveal them. The debate is far from settled, and that's what makes this so thrilling. Every new observation from the Planck satellite's painstaking maps to upcoming projects like the Simons Observatory brings us closer to cracking the case. Whether the cold spot is a cosmic glitch, a void, or something far stranger, one thing's certain: it's forcing us to question how well we truly know the universe. And in that uncertainty, there's magic, because if the answer does point to a multiverse, we're not just stargazers anymore. We're cosmic detectives piecing together clues from a crime scene that spans existence itself. Bubble universes might sound like something out of a child's imagination, but they're actually one of the most compelling frameworks in modern cosmology. The idea comes from eternal inflation theory, which suggests that our universe isn't just expanding, it's doing so exponentially, with pockets of space pinching off into their own self-contained realities. These bubbles form when quantum fluctuations trigger localized expansions, each one inflating into its own cosmos with its own unique physics. Picture a pot of boiling water, with bubbles constantly forming, rising, and popping, except in this case the bubbles don't pop. They grow, drift, and sometimes even collide. Now, here's where it gets wild. If our universe is one of these bubbles and others are out there floating in the multiverse foam, what happens when two of them meet? Simulations show that a collision between bubble universes wouldn't be like a car crash or an explosion. Instead, it'd be more like two soap bubbles merging, gentle at first but with profound consequences. The walls of these bubbles are regions where the fundamental forces shift dramatically, and when they intersect, the energy release could leave behind ripples in space-time itself. Scientists have modeled these collisions, and the results are astonishing. A universe-on-universe impact wouldn't just vanish without a trace. It could create distinct patterns in the cosmic microwave background, concentric rings of temperature variations, like the ripples from a pebble dropped in a pond. These imprints wouldn't be random noise, they'd have specific, measurable signatures, like a fingerprint pressed into the fabric of reality. Some researchers argue we might have already spotted hints of these patterns in the CMB data, subtle anomalies that don't quite fit the standard model of cosmic evolution. But how do you distinguish a multiverse collision from other cosmic phenomena? That's where the simulations get even more fascinating. Unlike random fluctuations or voids, bubble collisions would leave behind symmetrical distortions. Think of a bullseye target stamped onto the sky. Teams at places like the Perimeter Institute and Cambridge have spent years refining these models, mapping out how different collision angles, energy levels, and bubble sizes would alter the observable aftermath. The goal: to create a cosmic matchbook of possible collision signatures, so that when telescopes like the James Webb or future CMB probes spot something unusual, we'll know whether we're looking at a glitch or a gateway. The implications are staggering. If we ever confirm a bubble collision imprint, it wouldn't just prove the existence of other universes, it would rewrite our understanding of reality's architecture. Suddenly, the Big Bang isn't the only beginning. It's just one event in an endless cycle of creation and collision. And if collisions happened once, they could happen again. Right now, another universe might be drifting toward ours, invisible but inevitable, like a ship moving through fog. The cosmos isn't static, it's dynamic, alive with possibilities. And the next great discovery might not come from looking deeper into our universe, but from finding the marks left by something beyond it. String theory turns the multiverse from a wild idea into a mathematical inevitability. But to understand why, we need to rethink reality's very foundation. Forget the tidy 3 dimensions we experience daily. String theory suggests the universe has at least 10, maybe more. These hidden dimensions aren't just empty space, they're the stage for an unimaginable cosmic dance, where objects called branes, short for membranes, float like sheets of paper in a higher dimensional wind. And here's the game changer. Our entire universe might exist on one of these branes, a 3-dimensional island adrift in a vast, unseen ocean. Now picture 2 of these branes drifting toward each other in the higher dimensional void. When they collide, the energy released could be cataclysmic enough to birth an entirely new universe. Sound familiar? That's because some physicists argue our Big Bang might have been exactly that, a brane collision. Think of it like clapping your hands together. The force creates heat, sound, and motion. In the same way, when branes smash, they could unleash the heat of a universe's birth, the sound of space-time stretching, and the motion of expansion we now call the cosmos. The math behind this is staggeringly elegant. String theory's equations allow for branes of different dimensions, some like infinite planes, others curled into loops, all vibrating at frequencies that determine the laws of physics within them. Collisions between branes wouldn't just be random chaos, they'd follow precise patterns like waves crashing in predictable rhythms. This means a multiverse wouldn't be a free-for-all of random universes, but a structured, almost musical arrangement of realities, each with its own vibrational tune. But how could we ever prove something so abstract? Here's where it gets tangible. If our universe began with a brane collision, the echo of that impact might still linger. Just as earthquakes leave aftershocks, a brane collision could have sent gravitational waves rippling through space-time waves so powerful they distort the fabric of reality itself. Future detectors like the Laser Interferometer Space Antenna LISA might one day catch these whispers from the birth of existence. And there's another clue hiding in plain sight: dark energy. The mysterious force accelerating the universe's expansion fits eerily well with some brane world models. Imagine our brane flexing or stretching in the higher dimensional void, tugging on space-time like a rubber sheet. That tension could mimic the effects we attribute to dark energy, a cosmic puzzle piece snapping into place. Critics argue string theory's lack of experimental proof keeps it in the realm of speculation, but that misses the point. Science often races ahead of technology, theorizing what we can't yet observe. A century ago, black holes were mere pencil scratches on Einstein's equations. Today, we photograph them. Brane collisions might follow the same path from mathematical curiosity to observable fact. So when you hear multiverse, don't just picture alternate versions of yourself. Picture a cosmic symphony where branes collide like cymbals, ringing out new universes with every strike. Our reality might be one note in an infinite composition, played in dimensions beyond sight but not beyond imagination. And if string theory's right, the next collision could be just a dimension away waiting to rewrite everything we know. What if the Big Bang wasn't the beginning, but the echo of something far more extraordinary? For decades, we've pictured it as the ultimate starting gun, the moment when space, time, and matter burst into existence from a single, unimaginably dense point. But what if that point wasn't a beginning at all? What if it was the aftermath of a cataclysmic collision between universes? This radical idea turns cosmology on its head. Imagine 2 cosmic branes, those higher dimensional membranes from string theory floating in an 11-dimensional void. They drift closer, pulled by forces we can't perceive until impact. The energy of that collision doesn't just vanish, it ignites. Like striking a match in a dark room, the clash could have unleashed the searing heat and rapid expansion we now call the Big Bang. Suddenly, our universe's birth isn't an isolated event. It's a cosmic car crash, one of countless in an eternal cycle of collisions and rebirths. The math behind this is both elegant and mind-bending. In brane cosmology, when two universes collide, their energy doesn't just dissipate, it gets funneled into creating new space-time. Picture two sheets of fabric slapping together. The wrinkles and folds that form could become galaxies, stars, even the atoms in your body. This isn't just poetic imagery. Simulations show such collisions would produce the same uniform cosmic microwave background and large-scale structure we observe today. It's as if the universe's blueprints were drawn by the shockwaves of a multiverse smash-up. But here's where it gets even stranger. If the Big Bang was a collision, there might be evidence hiding in plain sight. Some models predict that such an event would leave behind gravitational wave, fingerprints, ripples in space-time far more powerful than those from black hole mergers. These primordial waves would have stretched and faded over billions of years, but next-generation telescopes might still catch their whispers. Then there's the universe's puzzling flatness. The fact that space-time isn't curved but eerily balanced could be a natural consequence of branes flattening each other out during impact, like rolling pins smoothing dough. Of course, not everyone's convinced. Critics argue that without direct proof, brane collisions remain in the realm of speculation. But consider this, before the Higgs boson was discovered, it was just scribbles in a physicist's notebook. Before the cosmic microwave background was detected, it was a theoretical ghost. Science often races ahead of proof, lighting the path for future discoveries. If this hypothesis holds, it reshapes not just our origin story, but our destiny. A collision-triggered Big Bang implies the multiverse isn't static, it's dynamic, even violent. Other universes might be out there right now, hurtling toward ours. The next cosmic rebirth could be written in the stars, waiting for us to decode it. So when you look up at the night sky, remember, you're not just seeing the aftermath of an explosion. You might be gazing at the scar of the greatest collision in existence, the one that started it all. If we want to understand how universes collide, we can't just stare at the sky. We have to recreate the chaos in supercomputers. Today's simulations are like cosmic time machines, letting scientists rewind the multiverse's clock to moments before impact, then play it forward frame by frame. The results, jaw-dropping visualizations where space-time itself twists like taffy, revealing secrets no telescope could ever spot on its own. Take the work happening at institutions like the Perimeter Institute or Cambridge. Teams there feed Einstein's equations into massive clusters of processors, programming virtual universes with different laws, some with stronger gravity, others with extra dimensions, then smash them together at a fraction of light speed. What emerges isn't random noise, it's a symphony of gravitational waves, temperature ripples, and warped space, all carrying the fingerprints of a collision. One groundbreaking simulation showed two bubble universes grazing each other. Instead of a catastrophic explosion, their boundaries merged like ink dispersing in water, creating shockwaves that propagated outward in perfect concentric rings. These rings aren't just pretty visuals, they're precise predictions. If a real collision left similar marks in our cosmic microwave background, we'd expect cold spots surrounded by faint, circular imprints, almost like a bullseye painted across the cosmos. The real breakthrough came when researchers compared these digital collisions to actual CMB data. Certain anomalies, like the infamous cold spot, aligned eerily well with the simulated aftermath. It's like finding a suspect's DNA at a crime scene. The match isn't perfect yet, but with each iteration, the simulations grow sharper, accounting for variables like dark energy's push and the quantum froth of the early universe. Future models aim to go even further, incorporating string theory's hidden dimensions. Imagine simulating branes colliding in 10D space, then projecting their aftermath into our 3D world to see what traces they'd leave. The computational cost is staggering, but the payoff could be revolutionary. A universal Rosetta Stone to decode whether our universe bears the scars of a multiverse crash. So next time you hear about astronomers mapping the cosmos, remember, some of the boldest discoveries aren't made with telescopes. They're born in lines of code where scientists play gods, hurling virtual universes at each other to uncover the deepest truth of all, that we might not be alone in the grandest sense imaginable. Gravitational waves aren't just ripples in space-time, they're the universe's way of whispering its secrets. Imagine dropping a pebble into a still pond and watching the circles spread outward, carrying traces of the splash that created them. Now picture that on a cosmic scale, where the pebble is a collision between universes and the pond is the very fabric of reality. These waves could be our best shot at eavesdropping on a multiverse smash-up that happened billions of years ago, hidden in plain sight until now. The key lies in their purity. Unlike light, which gets scattered or absorbed by dust and gas, gravitational waves travel cleanly across the cosmos, untouched by the obstacles in their path. They're the ultimate cosmic messengers, carrying undistorted information from events too distant or violent for telescopes to see directly. And the wild part: we've already proven we can detect them. LIGO groundbreaking detection of black hole mergers in 2015 was just the beginning, a proof of concept that space itself can ring like a bell. But the gravitational waves from a universe-scale collision would be different. They wouldn't last milliseconds, they'd resonate across eons like the deep, lingering hum of a gong struck in the dawn of time. That's where the next generation of observatories comes in. Projects like the Laser Interferometer Space Antenna, or LISA, aim to catch these primordial waves by launching a trio of satellites into orbit, forming a gravitational wave ear with arms millions of miles long. Unlike ground-based detectors, which are limited by Earth's noise and size, LISA could sense low-frequency waves, the kind predicted to linger from events like brane collisions or cosmic inflation. Think of it as tuning a radio from static to a clear signal, one that might carry echoes of the multiverse itself. But how would we recognize a collision's signature in the data? Simulations suggest it would look like a slow crescendo, a wave that builds in intensity over months or even years, rather than the sharp spikes of black hole mergers. Some models even predict a distinct chirp pattern, a gravitational fingerprint unique to universe-scale impacts. And if that pattern matches anomalies in the cosmic microwave background, like the cold spot, that's when the pieces start falling into place, linking the abstract math of string theory to observable reality. Of course, the challenge is staggering. The waves from an ancient collision would be faint, stretched by the expansion of the universe into near silence. Detecting them is like trying to hear a single raindrop in a hurricane. But here's the thing, science thrives on impossible hunts. 50 years ago, the idea of photographing a black hole seemed laughable. Today, we've done it. The same relentless curiosity that brought us this far could soon turn speculation into fact, revealing not just how our universe began, but what it might have crashed into along the way. So when you hear about gravitational waves, don't just think of black holes or neutron stars. Think bigger, think older, think of space-time itself trembling from a collision so vast, its echoes are still traveling, still reachable, if only we learn how to listen. The universe isn't silent, it's telling us a story, and the next chapter might be written in vibrations we're only now learning to decode. The universe is supposed to expand in all directions equally, a grand, symmetrical dance of galaxies drifting apart. But something bizarre is happening on the edges of our observable cosmos. Hundreds of galaxy clusters aren't just expanding with the rest of space. They're racing in a single, unnerving direction, as if being tugged by an invisible hand. Astronomers call this dark flow, and it's one of the most puzzling mysteries in modern cosmology. Imagine throwing a handful of leaves into a river. Most drift freely with the current, but a few cling together, moving stubbornly upstream against the flow. That's what dark flow looks like, except instead of leaves, it's entire galaxy clusters spanning millions of light years, all streaming toward a point beyond the cosmic horizon. The first hints of this anomaly came in 2008, when researchers analyzing data from the Wilkinson Microwave Anisotropy probe noticed clusters moving at staggering speeds, nearly 2 million miles per hour, toward a region of space near the constellations Centaurus and Vela. At first, critics dismissed it as a measurement error or an artifact of incomplete data, but later studies, including observations from the Planck satellite, only deepened the mystery. The flow persisted, defying expectations with its sheer scale and consistency. So what could possibly exert enough gravitational pull to move galaxies like marbles on a tilted table? One radical explanation points to the multiverse. If another universe exists beyond the limits of what we can observe, its massive structures, perhaps a supercluster of galaxies dwarfing our own, might be yanking on ours through some unseen gravitational link. Picture two boats floating near each other in a foggy harbor. Even if you can't see the other vessel, you'd feel its wake rocking your own. In this scenario, dark flow could be the cosmic equivalent, a gravitational wake from a neighbor we'll never glimpse directly. Not everyone buys the multiverse angle, though. Skeptics argue the flow might stem from irregularities in the early universe, like a primordial density fluctuation left over from inflation. Others suggest it could be the ghostly influence of a region where space-time itself is warped, funneling matter like water down a drain. The challenge is separating the signal from the noise. Our universe is a messy place, full of local gravitational pulls from superclusters and voids that complicate the picture. Teasing out a coherent flow from that chaos requires painstaking analysis, and even then, the data remains hotly debated. Yet the implications are too tantalizing to ignore. If dark flow is evidence of a neighboring universe, it would revolutionize our understanding of reality's boundaries. We're not just talking about parallel worlds in some abstract theoretical sense. We're talking about a concrete gravitational signature, a fingerprint left on our cosmos by something vast and alien, lurking just beyond the veil of observation. Future experiments like deep field surveys with next-generation telescopes could settle the debate by mapping the flow's precise trajectory or uncovering new anomalies in the cosmic microwave background. For now, dark flow remains an open question, a cosmic whisper we can't quite decipher. But that's the thrill of science at the edge of knowledge. Every unexplained phenomenon is a potential crack in reality's facade, offering a glimpse of what might lie behind it. And if that crack leads to another universe, well, suddenly the cosmos feels a lot more crowded, and a whole lot stranger, of course. Not every cosmic anomaly is a gateway to the multiverse. Sometimes a cold spot is just a cold spot. Before we rewrite the laws of physics, it's worth considering simpler explanations for phenomena like the cold spot or dark flow. The scientific method demands we rule out the ordinary before leaping to the extraordinary, and the universe is full of naturally occurring oddities that don't require parallel realities to explain them. Take the cold spot's most mainstream rival, the supervoid hypothesis. Vast, sparse regions of space where galaxies are unusually scarce could create temperature dips in the cosmic microwave background simply by lacking the matter to absorb and re-emit energy. It's like holding an ice cube against your skin. The absence of heat registers as cold. Some studies suggest the cold spot overlaps with a potential void spanning hundreds of millions of light years, though even this theory has gaps. Voids that large are rare, and their predicted temperature effects don't always match the observed extremes. Still, it's a compelling counterargument, one that doesn't require invoking other universes. Then there's the chaos of the early cosmos itself. The universe wasn't born perfectly uniform. quantum fluctuations during inflation seeded tiny density variations that grew into today's galaxies and voids. Statistically, some regions were bound to end up hotter or colder than average purely by chance. The cold spot could be a cosmological dice roll, a 1 in 100 fluke that stands out simply because we've mapped the sky in such exquisite detail. It's the same reason you might flip 10 heads in a row with a fair coin. Unlikely, but not impossible. Even dark flow has terrestrial explanations. Instrumental errors, incomplete data, or local gravitational pulls from known superclusters could mimic the appearance of a coordinated motion. The universe isn't a static backdrop. It's a dynamic web of moving parts, and teasing apart genuine anomalies from observational noise is like listening for a whisper in a windstorm. This isn't to dismiss the multiverse hypothesis, it's to refine it. Science thrives on skepticism, on the relentless questioning of even the most tantalizing ideas. Every potential crack in reality's facade must be stress-tested against mundane explanations, because that's how we separate coincidence from revelation. The cold spot might yet prove to be a bruise from a cosmic collision, or it might fade into the statistical noise as our telescopes grow sharper. Either outcome teaches us something vital. The beauty of cosmology is its humility. It reminds us that the universe owes us no easy answers, that the truth is often stranger and subtler than our grandest theories. So while we chase shadows at the edge of existence, we're also learning to see the ordinary in extraordinary new ways. After all, even if the cold spot is just a void, it's still a window into the universe's untold stories. And sometimes the most profound discoveries aren't about finding new worlds, but seeing our own with fresh eyes. Quantum entanglement already bends our understanding of reality. But what if it's not just linking particles in our universe, but tethering them to versions of themselves in parallel worlds? Picture two entangled electrons, their fates intertwined no matter how far apart they drift in space. Now, imagine that connection stretching farther than we thought possible across the membrane of reality itself, tying one particle here to its counterpart in another universe entirely. This isn't just sci-fi speculation. It's a serious hypothesis some physicists call entanglement across the multiverse, and it could rewrite everything we know about quantum weirdness. Think of it like a cosmic version of a pair of walkie-talkies. Normally, when you separate them, they only communicate through radio waves within this universe. But what if one device could somehow transmit to another dimension? That's the gist of quantum entanglement across universes' particles, talking instantaneously, not just across light years, but across realities. The math behind this is mind-bending, rooted in interpretations like the many worlds theory, where every quantum decision spawns a new universe. If all those alternate realities exist, why couldn't entanglement bridge them? Here's where it gets wilder. In some models, these cross-universe links could explain why quantum particles seem to know each other's states faster than light should allow. If they're not actually communicating through our space-time but through higher dimensions or parallel branes, the speed limit of light doesn't apply. It's like two ants on opposite sides of a folded piece of paper suddenly touching when the paper is bent. Their connection isn't through distance, but through a hidden dimension. But how would we ever test such a staggering idea? One clue might lie in the very experiments that first proved entanglement. If particles are linked across universes, their correlations could exhibit subtle anomalies, patterns that don't quite fit standard quantum mechanics. Some theorists suggest that carefully designed interference experiments, perhaps with ultra-precise photon detectors, might reveal faint echoes of influence from other realities. Others propose that gravitational wave observatories could one day spot ripples with no clear source in our universe, hinting at quantum interactions leaking in from elsewhere. Of course, skepticism is healthy. Critics argue this is speculation piled on speculation, that until we have concrete proof of other universes, cross-dimensional entanglement remains a beautiful thought experiment. But consider how many once impossible ideas, from black holes to the Big Bang, eventually became textbook science. The universe has a habit of outrunning our imagination. So next time you hear about spooky action at a distance, remember, the spookiness might not stop at our universe's edge. Those entangled particles could be whispering to versions of themselves in worlds we'll never see, weaving a web of connections far stranger than we've dared to dream. And if that's true, reality just got a lot bigger and a lot weirder. The idea of parallel universes isn't just confined to labs and lecture halls. It's exploded into pop culture, shaping some of the most iconic stories of our time. Take Marvel's Doctor Strange in the Multiverse of Madness, where the hero leaps through kaleidoscopic realities, each with its own twisted version of familiar faces. The film's dazzling visuals might be pure Hollywood, but the core concept, alternate worlds where choices branch into infinite outcomes, is ripped straight from the pages of quantum physics. Or consider Rick and Morty, the animated series that turns multiverse theory into a chaotic playground. When Rick boasts about infinite realities, he's not just spouting sci-fi nonsense. He's echoing the many worlds interpretation, where every decision spawns a new timeline, from trivial choices like what to eat for breakfast to universe-altering events. Even classics like The Twilight Zone and Sliding Doors have toyed with the idea that reality might be more like a choose-your-own-adventure book than a fixed path. Everything Everywhere All at Once took it further, blending alternate lives with emotional resonance, showing how the multiverse isn't just about wild physics, but about the weight of the roads not taken. These stories resonate because they tap into a deep human question. What if I'd made that left turn instead of a right? What if history had unfolded differently? Fiction lets us explore those possibilities without needing a particle accelerator. But here's the twist: sometimes art inspires science as much as the other way around. When Star Trek introduced handheld communicators in the 1960s, few imagined we'd one day carry smartphones. Similarly, the multiverse in pop culture doesn't just entertain, it primes our imaginations for real scientific leaps. Physicists like Michio Kaku have admitted that sci-fi sparks curiosity, pushing researchers to ask, could this actually work? The line between storytelling and hypothesis blurs. After all, string theory's hidden dimensions sound a lot like Interstellar's tesseract, and both leave us staring at the night sky wondering what else is out there. So next time you watch a character hop between dimensions, remember, it's not just escapism. It's a reflection of humanity's oldest itch, the need to explore beyond the horizon, even if that horizon is the edge of reality itself. And who knows, maybe one day the wildest multiverse tales will seem as quaint as Journey to the Moon does now. Until then, we've got popcorn, curiosity, and a universe of stories to keep us guessing. The idea of multiple worlds isn't some flashy modern invention. It's as old as human curiosity itself. Ancient Hindu texts like the Rig Veda, written over 3,000 years ago, described endless cycles of creation and destruction, with countless universes floating like bubbles in an infinite ocean. The Greeks pondered it too. Philosophers like Democritus speculated that an infinity of worlds must exist beyond our own, each with its own unique forms of life and matter. Even indigenous cultures, from the Navajo to the Aboriginal Australians, wove stories of dreamtime realms and spirit worlds existing alongside our own parallel realities, accessed through rituals, visions, or sacred landscapes. Fast forward to the Middle Ages, and the multiverse took on a theological twist. Scholars like Thomas Aquinas wrestled with whether God could create other worlds not as metaphors but as actual physical places. By the Renaissance, Giordano Bruno took it further, arguing that the stars were distant suns circled by their own Earths, each harboring life. For this radical vision, he was burned at the stake. Yet the seed was planted. The cosmos might be vaster and weirder than anyone dared admit. the scientific revolution turned speculation into equations. In the 1800s, mathematician Bernhard Riemann showed how space could curve into higher dimensions, hinting at unseen realms just beyond perception. Then came quantum mechanics in the early 20th century, shattering the illusion of a single, predictable universe. Suddenly, particles existed in multiple states at once, and physicists like Hugh Everett proposed that every quantum decision spawns new branches of reality, an infinite, many-worlds tree where every possible outcome plays out somewhere. Today, we stand on the shoulders of these visionaries, armed with telescopes and supercomputers instead of parchment and philosophy. But the core question remains unchanged. Are we alone in existence, or is our universe just one note in a grand cosmic symphony? From ancient seers to modern scientists, humanity's obsession with multiple worlds reveals something profound, not just about the universe, but about us. We've always longed to peek behind the curtain of reality to find out what or who might be staring back, and with each new discovery, the curtain gets a little thinner. Discovering that our universe has collided with another wouldn't just rewrite physics textbooks, it would force us to confront existential questions we've never had to face before. If we're not alone in the multiverse, does that make humanity more significant or utterly insignificant? On one hand, surviving a cosmic smash-up suggests we're resilient, like ants enduring an earthquake. On the other, it means we're living in what might be a celestial junkyard, a universe shaped by forces beyond our control or comprehension. The philosophical whiplash would be staggering. Then there's the elephant in the room, life. If collisions between universes are possible, could they have seeded life across realities? Imagine a scenario where organic molecules or even primitive organisms hitched a ride on the shockwaves of a collision, spreading like interstellar pollen. The idea isn't as far-fetched as it sounds. We already know extremophiles on Earth can survive the vacuum of space, but here's the darker flip side. What if another universe operates under laws of physics hostile to life as we know it? A reality where time runs backward or entropy doesn't exist might be uninhabitable to us, but what if something thrives there? The unsettling truth is, we'd have no way to predict whether our first contact with the multiverse would be a handshake or a warning sign, and let's talk about intent. If other universes exist, did they collide with ours by accident, or is there something, or someone orchestrating these encounters? The possibility raises thorny ethical dilemmas. Should we actively search for signs of colliding universes, or could poking at the fabric of reality attract unwanted attention? History isn't kind to civilizations that explore blindly. Think of the unintended consequences when Europeans crossed the Atlantic. Except this time, there are no oceans to sail back across if things go wrong. But perhaps the most profound question isn't about danger or discovery, it's about responsibility. If we're part of a multiverse, do we owe anything to other realities? Environmental ethics on Earth grapple with how we treat ecosystems and future generations. Now scale that up to cosmic proportions. Could meddling with the boundaries between universes, say, through advanced technology, unleash chain reactions we can't undo? It's not just about what we can do, but what we should do with that knowledge. For now, these ideas live in the realm of speculation. But science has a way of turning speculation into fact faster than we expect. Every time we've thought we were special, the center of the solar system, the only galaxy, the sole planet with life, the universe has humbled us, confirming a multiverse collision might be the next great humbling. And yet, there's a strange comfort in that. However vast and chaotic existence turns out to be, we're still here, asking the questions, tracing the scars, and daring to wonder what else is out there. Time dilation and wormholes sound like they're straight out of a sci-fi epic, but when you throw multiverse collisions into the mix, the line between fantasy and physics starts to blur. Picture this: if two universes collided, the sheer gravitational force of that impact could warp space-time so violently that it might tear temporary holes in the fabric of reality, shortcuts bridging distant points in space or even different dimensions. These wouldn't be your average cosmic potholes. They'd be like cosmic whirlpools swirling with energies we can barely comprehend, potentially bending time itself in ways that defy intuition. Take time dilation first. Einstein showed us that gravity doesn't just pull on objects, it stretches time. The stronger the gravity, the slower time ticks. Near a black hole, minutes could pass for you while years fly by elsewhere. Now, imagine the gravitational chaos of two universes smashing together. The resulting distortions might create pockets where time behaves erratically, speeding up, slowing down, or even looping back on itself. Some models suggest these zones could act like natural time capsules, preserving moments from the collision like insects trapped in amber. For an observer outside the chaos, it might look like a flickering film reel of the universe's history playing in fast forward or reverse. Then there's the wormhole angle. Normally, these hypothetical tunnels through space-time require exotic matter with negative energy to stay open, something we've never observed. But a multiverse collision could provide a shortcut. The energy released might briefly stabilize a wormhole's walls, like a lightning bolt carving a path through the sky. The catch: these portals would likely be unstable, snapping shut in nanoseconds or flooding anything passing through with lethal radiation. Still, the tantalizing possibility remains. If you could harness that moment of chaos, you might leap across universes or eras in the blink of an eye. Here's where things get really wild. If a wormhole linked two colliding universes, it wouldn't just bridge space, it could fuse their timelines. Suddenly, events from one reality might bleed into another, like ink seeping through wet paper. Imagine finding fossils of creatures that never evolved in your world, or stars that burn in colors physics says shouldn't exist. These wouldn't just be curiosities, they'd be living proof that the multiverse isn't just out there, it's tangled up with our own past. Of course, this is all speculative, straddling the edge of what equations allow and what experiments can test, but that's the thrill of frontier science. Every outrageous idea, from black holes to quantum entanglement, once sounded impossible until it wasn't. The difference now is that we're not just dreaming of wormholes or time warps. We're asking how a multiverse might build them for us, leaving behind clues in the wrinkles of space-time. And if we're right, the greatest time machine in existence might not be something we invent, but something we stumble across, a relic of the ultimate cosmic crash. Black holes are often seen as the universe's ultimate in points, cosmic pits where matter vanishes forever. But what if some of them aren't just dead stars that collapsed? What if they're relics of something far more violent, like the wreckage of a universe-scale collision? The idea isn't as outlandish as it sounds. When two universes smash together, the gravitational forces at play could twist space-time into knots so tight they leave behind black holes as permanent scars. Think of it like a car crash. The impact doesn't just leave dents, it can warp the frame beyond recognition. In the same way, a multiverse collision might not just bend space-time. It could rip it, crumpling regions so violently that they become gravitational traps. Some theories suggest these wouldn't be ordinary black holes, but ones with bizarre properties like unusual spins or masses that don't match any known stellar process. They'd be cosmic anomalies, fingerprints of a crash that happened long before stars even formed. This isn't just speculation. Recent discoveries about black hole mergers hint at something strange lurking in the data. When LIGO detected gravitational waves from colliding black holes, some of them had masses that shouldn't exist. Conventional astrophysics struggles to explain how black holes could grow so large so quickly in the early universe. But if those black holes weren't born from stars at all, but forged in the chaos of a multiverse collision, suddenly the numbers start making sense. Here's where it gets even more intriguing. If collision-born black holes exist, they might cluster in specific patterns, like shrapnel from an explosion. Astronomers have already spotted strange groupings of supermassive black holes at the centers of galaxies, some with orbits that defy easy explanation. Could these be the remnants of ancient cosmic crashes lingering like bullet holes in the fabric of space? Simulations suggest that during a universe collision, black holes wouldn't just form randomly, they'd align along shockwaves, creating detectable signatures in their distribution. The hunt for these relics is already underway. Next-generation telescopes like the Laser Interferometer Space Antenna and the James Webb could soon spot black holes with the wrong spin, the wrong mass, or sitting in the wrong places. Each one could be a clue, a breadcrumb leading us back to the moment our universe tangled with another. And if we find them, it would mean black holes aren't just graves for dead stars. They're monuments to the violence that shaped existence itself. Imagine future cosmologists not with shovels and brushes, but with quantum computers and AI algorithms, sifting through exabytes of cosmic data like digital archaeologists uncovering an ancient catastrophe. Their excavation site, the entire observable universe where every anomaly in the cosmic microwave background, every skewed galaxy cluster, and every rogue gravitational wave could be a fragment of evidence from a multiverse collision billions of years ago. This wouldn't just be astronomy, it would be interstellar forensics reconstructing an event that reshaped reality itself. Think of it like piecing together a car crash without witnesses. Investigators measure skid marks, study debris patterns, and analyze damage to calculate the speed, angle, and force of impact. Now replace the cars with universes, the skid marks with temperature fluctuations in the CMB, and the debris with strange black hole distributions. The tools may differ, but the goal is the same: reverse engineering a cataclysm from its scars. Some of the most crucial artifacts would be polarization patterns in the CMB subtle swirls that could indicate gravitational waves from the collision. These wouldn't be random, they'd form concentric rings or spiral signatures, like the ripples from a stone tossed into a pond. Future telescopes might even detect bruises where space-time was stretched thin during impact, leaving regions with unnaturally low density. And then there's the cosmic equivalent of blood spatter, high-energy particles or unusual radiation patterns that don't fit standard models, hinting at exotic physics from another universe's laws bleeding into ours. But here's the twist: unlike a crime scene on Earth, the evidence isn't frozen in time. The universe keeps evolving, stretching and distorting the clues. It's as if the wreckage were slowly dissolving while investigators work. That's why multiverse archaeology would need time machines of a sort, simulations that rewind cosmic expansion, peeling away eons to reveal the collision's original fingerprint. Teams might train neural networks to spot hidden correlations in data, or use quantum entanglement to probe higher dimensions where traces of the crash could linger. The most thrilling possibility: finding foreign matter that doesn't belong, particles with properties violating our universe's known laws. Imagine carbon dating a relic and discovering its atoms have the wrong half-life, or detecting a galaxy spinning backward against cosmic norms. These wouldn't just be oddities, they'd be smoking guns, proof that something from outside our reality left its mark. Of course, skeptics would demand airtight proof. A single anomaly could be a fluke, but a constellation of them, strange particles, gravitational echoes, and skewed geometries all aligning with collision models, would be harder to dismiss. It's the difference between finding a lone dinosaur bone and unearthing an entire fossilized ecosystem. So picture scientists centuries from now assembling the ultimate cosmic jigsaw. Each piece they slot into place wouldn't just reveal a past collision, it would hint at whether another might loom in our future. Because if universes can crash once, they can crash again. And next time, we might not need archaeology to spot it, we might feel it coming. The multiverse isn't just a scientific puzzle, it's a philosophical battleground where the very definition of proof is up for debate. On one side, you've got thinkers like Max Tegmark, who argue that the math doesn't lie. If multiple universes emerge naturally from equations as solid as quantum mechanics and inflation, why dismiss them just because we can't touch them yet? History's full of ideas that started as wild speculation, black holes, tectonic plates before evidence caught up to these physicists. The multiverse is no different. It's not science fiction, it's science waiting for its moment. But then there's the opposition, led by critics like Paul Steinhardt, who call the multiverse a theory of anything. If you can't falsify a claim, if no observation could ever disprove it, does it even count as science? The worry is that without testable predictions, the multiverse might slip into the realm of metaphysics, more philosophy lab than physics lab. It's a tension as old as cosmology itself. How far can theory stretch before it snaps under the weight of untestable speculation? The debate gets even thornier when you consider what evidence might look like. Sure, anomalies like the cold spot or dark flow are tantalizing, but are they smoking guns or just cosmic Rorschach tests? Critics point out that humans excel at finding patterns even where none exist. The constellations are a perfect example. We saw bears and hunters in random stars. Could the multiverse be the ultimate case of apophenia, our brains wiring meaning into noise? Yet breakthroughs often lurk in the gray areas. Remember the cosmic microwave background's discovery in the 1960s. At first, it seemed like mundane static, until it revolutionized our understanding of the Big Bang. The same could be true for multiverse hints. Maybe we're not seeing gaps in the data, but the edges of a reality we're only beginning to decode. What's clear is this: the multiverse forces us to confront the limits of the scientific method itself. Can a theory be valid if its proof lies forever beyond our cosmic horizon? The answer might not come from telescopes or equations, but from redefining what it means to know something. Until then, the multiverse remains the ultimate thought experiment, a mirror held up to science, reflecting our deepest hopes and uncertainties about the fabric of existence. Let's tackle the elephant in the room. No, a multiverse collision wouldn't turn Earth into cosmic confetti overnight. One of the biggest myths out there is that a universe-on-universe smash-up would mean instant doom for our little blue planet. The truth, it's way less Hollywood and way more subtle. Think of it like this: if two oceans merged, the fish in one wouldn't suddenly explode. They might not even notice the water around them had changed. A collision between universes would unfold on scales so vast and timelines so long. Human lives would flicker by like fireflies before the first gravitational ripples even reached us. Then there's the fear that a collision would rewrite physics overnight, turning gravity into spaghetti or making atoms forget how to bond. Reality's rulebook is stubborn. Even if another universe with different laws bumped into ours, the changes would likely be isolated to the borders where they touched, like two languages blending at the edges of neighboring countries. Your coffee wouldn't suddenly start boiling at room temperature, though that would solve a lot of morning caffeine emergencies, another classic misconception. That we'd see the other universe like some glowing portal splitting the sky. In reality, the effects would be hidden in the fine print of cosmic data, tiny temperature dips in the CMB, odd galaxy movements, or gravitational waves with weird signatures. It's less shock and awe and more forensic science on a universal scale. And let's debunk the idea that collisions are rare, one-off events. If the multiverse is real, these crashes could be as common as fender benders in a crowded parking lot, just happening over billions of years. Our universe might already be a patchwork of past collisions, their scars faded into the background like ancient battlefield wounds. So no, a multiverse collision wouldn't vaporize your commute or turn the sun purple. But it might leave clues in the fabric of space-time, waiting for us to decode them. And honestly, that's way cooler than an apocalypse. The universe doesn't do flashy disasters. It whispers its secrets in math and light for those patient enough to listen. The hunt for proof of multiverse collisions is about to leap from theoretical daydreams to real-world detection. and the tools we're building to catch these cosmic fingerprints are nothing short of extraordinary. Leading the charge is the Laser Interferometer Space Antenna, or LISA, a mission so precise it could detect gravitational waves from the dawn of time itself. Slated for launch in the 2030s, this trio of spacecraft will form a giant triangle in orbit, with each side stretching 2.5 million kilometers. That's like building a violin the size of the solar system, tuned to hear the faintest whispers of the universe's deepest secrets. What makes LISA so revolutionary? Current ground-based detectors like LIGO are incredible, but they're limited to high-frequency waves from relatively recent events like black hole mergers. LISA, floating free of Earth's seismic noise, will catch low-frequency waves, the kind that could carry echoes of universe-scale collisions from billions of years ago. Picture trying to listen to a symphony with only the piccolos audible. LISA hands us the bass notes, the resonant hum of cosmic history. And if those waves bear the signature of a brane collision or a bubble universe impact, that's when the textbooks get rewritten. But LISA isn't working alone. On the ground, the Simons Observatory in Chile's Atacama Desert is mapping the cosmic microwave background with unprecedented resolution, scanning for those telltale swirls or cold spots that might betray a multiverse encounter. Meanwhile, next-generation telescopes like the James Webb's successors will peer into the cosmic dark, hunting for anomalies in galaxy distributions or bizarre gravitational lensing that can't be explained by ordinary matter. The real game-changer, though, might be quantum sensors. Labs worldwide are developing devices so sensitive they could detect fluctuations in space-time itself, potentially picking up residual vibrations from ancient collisions. It's like dusting for fingerprints on a universal scale, except the dust is the fabric of reality, and the prints might belong to another universe entirely. We're standing on the edge of a paradigm shift, closer than ever to answering whether our universe is one or many. These experiments aren't just gadgets, they're time machines letting us eavesdrop on the birth pangs of existence. And if they find what they're looking for, the greatest discovery in human history won't be a new particle or planet, it'll be proof that we've been sharing the cosmos all along. What if our planet had formed right in the epicenter of a multiverse collision, a cosmic border town where two realities bled into one? Picture a world where the night sky doesn't just show stars, but shimmering fractures where the laws of physics glitch like a corrupted video file. Trees might grow in fractal patterns, their branches splitting into impossible geometries under the influence of competing gravity. Oceans could pulse with bioluminescent tides as exotic particles from the other universe interact with our water. Life here wouldn't just adapt, it would evolve into forms we can barely imagine, straddling the boundary between two sets of natural laws. Take something as basic as sunlight. In a collision zone, light from our sun might mix with radiation from the other universe, creating twilight bands where shadows behave erratically, stretching in two directions at once or flickering like candle flames in a draft. Plants could develop leaves that photosynthesize multiple light spectra, some visible only in the overlapping reality. Animals might evolve dual sensory organs, eyes tuned to our wavelengths alongside entirely new receptors for whatever passes as light in the neighboring cosmos. Imagine birds navigating by gravitational anomalies instead of magnetic fields, or microbes thriving on energy gradients that shouldn't exist in our universe alone. Then there's the ground beneath your feet. In a universe-mingling region, matter itself could become unstable. Rocks might briefly turn translucent as atoms flirt with alternate quantum states, or soil could ripple like liquid when vibrations from the other reality resonate through it. Cities built here would need adaptive architecture, buildings with self-repairing materials that recalibrate as local gravity fluctuates, or bridges engineered to withstand sudden shifts in tensile strength when the fabric of space-time glitches. But the most profound changes would happen at the smallest scales. DNA replication in collision zones might incorporate exotic nucleotides from the other universe, leading to organisms with entirely new biological building blocks. Enzymes could catalyze reactions that violate our chemistry's rules, creating life forms that metabolize impossible substances. Some organisms might even develop quantum entanglement with their counterparts in the other reality, sharing states across dimensional lines like cosmic twins. Of course, survival in such a place wouldn't be peaceful coexistence, it'd be an evolutionary arms race. Predators could exploit dimensional rifts to ambush prey from unseen angles, while prey might evolve reality camouflage that subtly shifts their appearance between universes to confuse hunters. Ecosystems would balance on a knife's edge, where every adaptation strains against the chaos of competing physical laws. Yet amid this turbulence, there's breathtaking potential. A collision zone could become nature's ultimate laboratory, birthing innovations no single universe could produce alone. Medicines might harness hybrid molecules that heal by altering quantum probabilities, or energy systems could tap into the friction between realities. The very concept of life would expand beyond Earth's template, proving that biology isn't just a local phenomenon, it's a universal principle, able to root itself even in the cracks between worlds. So while we're lucky to live in a stable corner of our universe, part of you has to wonder, what revolutionary forms of existence are thriving right now in those violent, glorious borderlands where realities collide? The answer could rewrite not just our science, but our sense of what's possible in existence itself. If proof of a multiverse collision were discovered tomorrow, the shockwaves wouldn't just ripple through labs and universities, they'd reverberate through temples, churches, and sacred texts worldwide. For some faith traditions, the idea of multiple universes might feel like a direct challenge to their cosmology. Take Christianity, where the concept of a single, divinely created universe has been central for centuries. A multiverse could force a re-examination of passages like Genesis, not as the story of the creation, but of a creation, one act in an endless divine play. Yet far from rejecting the idea, many theologians might embrace it as evidence of God's boundless creativity. After all, if a single universe reflects divine glory, wouldn't an infinite tapestry of them magnify that glory exponentially? Eastern philosophies, on the other hand, might greet the news with a knowing nod. Hinduism's ancient texts already describe countless universes floating like bubbles in an endless ocean, each with its own cycle of creation and destruction. The Vedas speak of Brahma dreaming worlds into existence, echoing the modern bubble universe hypothesis with eerie precision. Buddhism's emphasis on infinite realms of existence, some parallel, some nested, could seamlessly accommodate a multiverse, framing it not as a disruption but as validation of long-held intuitions about reality's layered nature. But the real turbulence would come in traditions with linear, singular cosmologies. Imagine explaining multiverse theory to a culture whose creation myth centers on a single, pivotal event. A world egg cracking open or a deity sculpting the earth from clay. The cognitive dissonance could mirror the upheaval of the Copernican revolution, when Earth was dethroned from the center of the cosmos. Back then, the Church initially condemned heliocentrism as heresy, only to later reconcile it with faith. A similar reckoning might unfold today, with religious scholars parsing whether multiverses contradict Scripture or simply expand its metaphorical horizons. Indigenous cosmologies, rich with stories of spirit worlds and dreamtime realms, might offer the most fluid adaptation. For the Navajo, whose tradition speaks of multiple layered worlds through which ancestors journeyed, or the Aboriginal Australians, whose songlines map a reality interwoven with unseen dimensions, multiverse science could feel less like a revelation and more like a rediscovery. These cultures have long operated with a pluralistic view of existence, where the boundaries between worlds are porous and alive. To them, physicists might not be pioneers, but latecomers to truths oral traditions have carried for millennia. The cultural fallout would be just as fascinating. Art and literature would explode with new metaphors, paintings of colliding cosmoses, novels where characters navigate the moral weight of infinite versions of themselves. Social movements might arise advocating for multiverse rights, questioning whether we owe ethical consideration to alternate realities and conspiracy theories. They'd have a field day if governments hid UFOs. Imagine what they'd do with proof of universe-shattering collisions. Yet history offers a reassuring pattern: humanity's capacity to absorb radical truths without unraveling. When Einstein shattered Newton's clockwork universe, we adapted. When quantum mechanics revealed a reality built on probabilities, we learned to live with the uncertainty. A multiverse wouldn't erase our stories, it would invite us to tell them anew, to find meaning not in being the center of existence, but in being part of something infinitely grander. The real test wouldn't be whether religions survive the revelation, but whether they and all of us can embrace a cosmos more wondrous than we ever dared to dream. The evidence for a multiverse collision is tantalizing but not yet definitive. On one side, we have cosmic oddities like the cold spot, an enigmatic patch of space that behaves like a bruise from an ancient impact. Mathematical models show such collisions would leave distinct imprints, and simulations align eerily well with what we observe. Gravitational wave detectors are tuning into frequencies that could carry echoes of universe-scale crashes, while anomalies in galaxy distributions hint at gravitational tugs from beyond our cosmic horizon. Even the laws of physics themselves might bear scars, with dark energy's mysterious push potentially tracing back to a long-ago collision. The pieces are there, scattered like clues in an interstellar detective story. Yet the case isn't closed. Skeptics rightly point out that cosmic mysteries often have mundane explanations. The cold spot could be a vast void, dark flow a measurement quirk, and those gravitational wave signals just noise in the data without direct proof, a smoking gun like foreign matter or a collision's gravitational chirp. The multiverse remains a breathtaking hypothesis, not confirmed fact. Science demands rigor, and right now the scales tip toward maybe rather than yes. But here's the beautiful part: the uncertainty itself is a gift. It means the cosmos still holds secrets, still whispers questions we haven't learned to answer. Whether our universe is solitary or one of many, whether it's born of a collision or not, the pursuit of these ideas stretches our imagination beyond limits. Every anomaly, every unexplained flicker in the data is an invitation to look deeper, think braver, and wonder bigger. So until the next great telescope snaps a photo or a quantum sensor catches a ripple from beyond, let's savor the mystery. The universe has always been stranger than we dreamed, and that's what makes it worth exploring. Keep looking up. The next revelation might be just over the horizon, waiting to rewrite everything we know. So what do you think? Has our universe already smashed into another? The evidence is wild, the theories mind-bending, but this debate is far from over. Drop your thoughts in the comments below. Do you buy the cold spot as a cosmic crash site? Or is it just a weird void? Maybe you've got a totally different take on dark flow or those bizarre black holes. Let's get spicy with it. Science thrives on disagreement, so don't hold back. And if this multiverse madness has your brain buzzing, hit that like button and subscribe. You won't want to miss what's coming next. We're diving even deeper into the cosmos's greatest mysteries, like what happens if we do find proof of other universes. Will it rewrite religion, spark new tech, or send philosophers into a tailspin? The answers might be closer than we think. Until then, keep looking up and questioning everything.